So good afternoon to one and all. I am Dr. Nandhini,
Yes, ma'am.
Associate Professor of Computer Science Department from Pondicherry University. Before going to start the session, I should thank the organization secretary for this conference, Dr. Indrani, Professor of Computer Science, and the committee members for having given this opportunity to present my research experience, what I gained on this area, optimization algorithms in engineering application. Before going to start the session, let me tell you the reason behind I have taken this title. Am I audible, Indrani?
Yes, ma'am, you are audible.
Yes. Shall I proceed?
Yes, madam. Yes, madam.
Yes. So before going to start, let's see the reason why we have gone for this presentation today. So today, if you see, many of the applications are there in our practical life we are facing daily. Whatever may be the scenario and the situation, and whatever may be the domain, like if it is sports or academic or any business, finally we are targeting about and we are aiming for ending up our work with the best result. So I hope you can understand the importance of this optimization in our practical scenario. And one other thing is, this is recently with respect to our research, mostly evolving area. Many of the researches are going on in this optimization algorithms. You can see so many papers in many of the websites. And one more reason is not only directly working on this optimization algorithms for our research purpose, you can consider these optimization algorithms for any of your research domain, whatever it may be. For example, if you are doing your work on image processing, otherwise any artificial intelligence, any area, wherever it is, even in machine learning, wherever it is, you can easily incorporate this optimization algorithms for doing your work with better performance. Hope you have seen many of them are doing their work in machine learning nowadays. So thereby, they are introducing this optimization algorithms for optimizing the feature selection, feature extraction, like so many things for doing this ML, that is machine learning research works. They are incorporating these optimization algorithms. So these are some of the reasons why I have taken this title for today's presentation. So this is what the ideas we are going to see out of today's presentation. So here, let me start up with introducing this optimization and applications and design procedure, the problem properties and different types of optimization and the taxonomy, and we will see what are the challenges we are having even now with these optimization techniques. So here in the domain, it is obvious that two broad areas has been given. One is optimization algorithm and another one is engineering application. We know so many applications are there, so many optimization algorithms are there, but still the students are not, the research scholars are not clear about what type of optimization algorithm is to be applied for what type of applications and how to model that applications. So there also they have so many confusions. So because of not getting and having clear-cut idea about how to apply and adopt this optimization algorithms into the problems, the model, what are they focusing is totally different from what are they expecting. So, and more than this, we know, we have seen so many optimization algorithms. Each and every algorithm are having their own unique pattern. So for the different applications, we should have an idea about that optimization algorithms to apply the suitable one on them. So this is what the main reason for having this presentation. Hope I will make up all these expectations for the participants. So let me start up with the entity introduction. The main entity here is optimization. So as we all know, so before going to start, let me tell you throughout this procedure, throughout this platform today, we are going to have this optimization only. So more frequently, I'm going to use this word optimization and application. Guys, you please don't confuse with these two entities. Optimization can be defined in multiple terms, out of which all, that is finding the best is the easiest and the best understanding of optimization. That is finding the optimal one out of n number of elements available in the space. So that is what optimization. So hereby they have given, the researchers have given standard definition for the optimization. So when we are finding for the best one out of the survival elements, based on its behaviors, we have to identify. So that behaviors is decided by the attributes of the entities. So those attributes here called technically as decision variables. So those decision variables we have to identify for whom we have to find out the best result for this problem. Then after by identifying this decision variable, on what you have to declare that those are giving the better performance. So for doing so, here we are having that function, which is nothing but objective function. Objective function is nothing but a targeting function, otherwise fitness function, which is giving you the that is multiple that is evaluation of that target what you are looking for. That is evaluation criteria of your application is being decided out of this objective functions. So if you take a problem in different scenarios, as we had seen that problems can be optimized. So with respect to the different factors, the problem may be optimized in different qualitative factors such as productivity, strength, reliability, longevity, efficiency, and utilization. These are some of the factors here given here. These are given as maximizing factors. So if you see that efficiency of your engine, any engine or your system, it is to be by default, it is to be improved. So it is to be maximized. So the simplest example of a profit and loss, if you see, always a profit is to be maximized and the loss is to be minimized. So in that way, with respect to the problem, not only the direct factors which is affecting your quality of the scenario, indirect factors and that is side effects of your problem also can be taken for fitting this or obtaining this objective function. So this is what you have to keep it in mind. So these ideas are helping you to design that objective function. So here, if you see that objective function is mathematically given as maximize f of x comma y and with some variables that is x and y. Okay. So here that f of x comma y is a function in terms of x and y, it is being defined. Then that decision variables, that is x and y, are the variables which are helping us to design the application. So x and y can be called as decision variables, otherwise design variables. I will tell you why these variables are named as either design or decision variables. Both are same. Okay. So here I have given one sample model, that is how a problem can be mathematically modeled. That is, one optimization problem can be mathematically modeled. Why it is called as? It is normally a problem, but here we are calling that as optimization problem. Why it is called so is, here as we know, optimization is nothing but we are going for finding the best one. On what condition we are trying for? Based on the constraints only, we have to find out the best one among the available states, that is state space. Number of states, which means state space. Number of solutions, that is nothing but state space. So those constraints are limiting the state space. So that is that feasible region whereby we have to search for our solution is being limited by these constraints. So that is what that feasible region. In this feasible region, so we have n number of solutions. Out of those n number of solutions, everything cannot be taken as the best one. So as we know, n number of students are there, but we are finding one student as the best student out of the mark or any other factors what we have used for evaluating them. In that case, here also out of that boundary, feasible boundary, any one solution is to be considered as the optimal one. So that is what the way this subjective function is helping us. So this is what the model we have to use for describing our application into this mathematical model. Okay, then you just see that diagram there. Here the same function, that is f of x comma y is here. That f of x comma y is defined here as sin of x and the cost of x. Guys, I'm not going to enter into max in depth. So without max, we cannot escape from our optimization area. But still, you have to have some basic understanding about how these are spread over this space. I mean this state space. Here, this x and y two axis is there. That is, that function is f of x comma y. The curve, that is cross-lined curves, is showing you that area, that is that state space where the solutions can be. You see there in that curved line, that is a crossed curved line, you'll be having ups and downs. In so many places it is moving up, in so many places it is coming down. And that values are starting, that is between the boundary 0 to 4. In this side also it is giving like 0 to -2. That is that the area where it is spreaded over. The sin of x and the cos of x function is. So here for this type of a problem, what we have to do is we have to start with one initial position whereby we have to find out the maximum value of that f of x comma y. So to reach that maximum value of this f of x comma y, since we are not known from where to start, here we have to start from initial position. That position may be arrived directly, otherwise by assumption also, like guessing also we can get. That is what a random value that you can generate for your problem. Then from there, by stepwise movement, we have to move ahead from one location to another location till you are getting the place where you are satisfying all your criteria, and also your result is giving you the best out of n available solution. That is what this picture is saying you. So this is what the concept which is clearly explaining us what is all about this optimization. So next, as I told you, we are going to map this optimization algorithm with this engineering applications. So before entering into that optimization algorithms, we will get an idea about how these engineering applications is and how it can be modeled to fit into the algorithms. That's what we are going to see. See here in the engineering application, you know, so many applications are there. Simple applications easily with available values, you can find that that application. If it is a vast application, vast in this that is in terms of its variables, in terms of the constraints, automatically, as you know, if that array is of one dimensional, easily you can find the solution or search the element. If it is of two dimensional, little bit that complexity is raising. If it is of a three dimensional, then again it is so automatically if the size is increasing, size in terms of here, that variables are increasing, and the constraints which is used in that application domain is increasing, automatically the complexity of the problem will be increasing. So in those cases, we have to carefully apply the suitable. Yes, yes.
ஸ்லைடு வந்து மூவே ஆகல மேம், அப்படியே இருக்குது. ஸ்லைடு மட்டும் கொஞ்சம் மூவ் பண்ணுங்க.
ஸ்லைடு மூவ் ஆகலையாப்பா?
மூவ் ஆகல.
ஸ்லைடு தெரியுதாம்மா?
ஸ்லைடு வியூல இருக்குது மேம், பட் அந்த ஃபர்ஸ்ட் அந்த டைட்டில் மட்டும் தான் இருக்கு. டைட்டில் மட்டும் தான் வியூ ஆகுது. நெக்ஸ்ட் பேஜ்
அப்படியா? Okay, I will share it again. இப்போ ஓகேவாப்பா?
எஸ் மேம், எஸ் மேம்.
Next slide movement is visible. Huh?
Okay. Yeah, yeah,
Is it
yeah.
okay? Okay.
Okay.
So this is what just before I discussed about this optimization. Sorry guys, I was not known about it. And so this is what is application. So here you see whatever may be the application, it is generally aiming for broad areas where that optimization is to be concentrated much. That is design of components of entire system and planning and analysis of existing system, engineering analysis and data reduction. So data reduction, that is the size, volume wise it is to be optimized, then control of dynamic system. So this is the broad view of the areas where that optimization is to be concentrated on the engineering application. And you see here some of the application, it's not only in one specific area, in medicine, bioinformatics, even in social network, our intelligence, I mean our artificial intelligence area, that is on the whole, some of that application problems are given here. Even in economics, scheduling applications, our applications also is listed out. These applications we can make use of for getting the best result for our problem. Okay. Here I have taken some of the applications and I have given for what we are working on these certain applications. That is automotive design, engineering design, and telecommunication and robotics. So if you take that automotive design, you know that the combinations of that material is to be what we are providing to be faster and lighter. It is to be fuel efficient and safer vehicles. It is to be there. So this is what the design motive of your automation. That is then in engineering design, in the civil engineering, if you see, so thereby structural and operational design of the buildings, factories, machines, these things are to be optimized. Okay, in the same way, even in telecommunications also, you know what is to be optimized because of the lines are there, which is connected among that nodes, is giving you that network. So in terms of a network, what is to be optimized, it is well known to us. Even in robotics also, robotics is nothing but it is a learning engine. So whereby how far efficiently this intelligence is imitating the human being, that is what its efficiency. So in terms of all these applications, a domain is has to shine well. So for doing so, what has to be done? That's what we are going to see. So here, what is given under each application domain is, so what are the factors we are aiming for out of that applications? So that is, it is the qualifying factor we are expecting out of this applications. Okay. So in order to get those qualifying factors out of that applications, first of all, we have to convert that engineering application into the optimal model. So for converting that into optimal model, we have certain procedure. That designing procedure is given here. So what is the purpose of doing this optimization? First of all, you have to identify. Then the design variables, the design, let's see what are all those one by one. So in the first slide itself, I told you about the design variables are that is design variables are decision variables. And one other thing is the constraints, then objective function. These three just before we had referred and seen over there with that that is optimization slide, and that variable boundaries to be set up. Then among all, after setting all these things, we have to go for finding that optimization algorithm. Then we have to get the solution and we have to evaluate the solution with the suitable factors. So this is what the procedure, whatever may be the application, if you wanted to target about optimizing it, it is to be followed. Following this, we are going to see in that is in terms each about that decision variables and objective functions, everything. So these decision variables, as I told you, it can be called as a design or decision variables. For example, if you see, if you are getting the good marks in a subject, suppose if a subject is having some subdivision in your test for a subject, if you have some subdivisions, those subdivisions can be taken as those two subdivisions are having their own marks, maximum marks. For example, if you take two subdivisions, 50 and 50 plus 50. So here for the first subdivision and the second subdivision, if you add up, then you will be getting the maximum mark of 100. So that has to come in the objective function. So here for designing this subject, evaluating the subject, two subdivisions has to be there. One subdivision you can take it as x, another one take it as y. The maximum of x should not exceed 50, that the y should not exceed likewise 50. Appo x less than or equal to 50 and y less than or equal to 50. And that objective function should be summing of this x and y. I mean x plus y. So this is the way, this is the simplest way of finding the optimal model for the problem. So this is the way you have to identify what may be the designing variables necessary for the problem what you have considered and how it can be collaborated with your objective function. So here, if you take that decision variables, those decision variables are deciding the behaviors of your application. So if a theoretical scenario is given to you, from that scenario, that behaviors of that problem is to be identified. So from them, what are the modules of how it is to be collaborated? Each modules in turn designed by what type of variables, that is behavioral factors, that is to be identified. That behavioral factors, how far it is taking its own attributes, each attributes, how far it can extend over the extended limit. So these are the ways from the given problem you have to identify the variables. So here they have defined it, what may be the design variables, list and every parameter related to the problem. So here why it is very important and significantly it is to be noted is, even if you miss any of the parameter of your problem, you may not get the expected one. You know well that if any one variable is missed out in your application, then implementing that problem is totally collapsed, totally waste of time. Then, so where it can be used in optimization procedure, for example, experience of the users. Suppose if you are going for any recommendation system, as what we are having lively in our Google engine, so many recommendation system is there. If you if you googling any of the sites like social network, immediately you will be getting the response when you are going for the next day. So that is based on the recommendation system. So and then sensitivity analysis, like everywhere, whatever may be the application, these are the variables to be identified at first. And not only identifying that variables, here we have to find out that the nature of that variables also. Nature of that variables may be binary, discrete or real numbers. So here these also playing a role in deciding the final value. And the example what we have discussed, that is getting the best mark or the highest mark in a subject by a student. So thereby that mark can be 80.5, 82.5, like so it may come. So that's why it is a real value. And also it is a discrete value. Discrete in the sense it is not continuous. So continuous and discrete, we will say how far it can be, and it is not at all binary. So in that way you have to identify. That means out of the values what are we going to receive for the variables, also we have to think about that variables when it is being designed for the application. Hope I am making you to understand. Here not only identifying the variables, you have to understand the values what is going to be assigned to those variables. So that also playing the role here. Okay, then constraints. Constraints are nothing but these are the limiting factors, that is wherever search space can be, that is being limited by this constraint. Search space can be, that is being limited by our constraint. Okay, so here two types of constraints are there, that is inequality constraint and equality constraint. You know that inequality less than or equal to, greater than or equal to, like so it may, and equality you know. So here in finding this optimization, here we are going to find the best only. We are not known what may be the best. See, try to understand, we are not known what may be the best. We are going to find the best. Even if you reach 100, you never stop. You may think that 101 is the best. So that means if, unless otherwise it is declared that what may be the target you are looking for, otherwise the searching procedure will be extended. So in that case, in this inequality constraints, so here if you are reaching that 100 in general, this 100 is the maximum value. So thereby you can stop. Suppose if you reach that 0, you can stop if it is the case of a minimization. But this is giving you the support in finding the optimization. The reason why is, so if you take that is 100 is the maximum. If I get 98 or 99, I can say that myself is the best one. But if it is the equality constraint, only I should, if I get the 100, then only I can declare that I am getting the best, I am getting the answer for this problem. So that is the problem with this equality constraint. So if you have this type of equality constraint in your problem, you have to carefully work for getting the solution when it is being optimized. Then next to that, objective function. So after deciding that design variable and this constraint, we have to go for those two terms, those two parameters are helping to finding the best one. That best one is being obtained by this objective function. So either it can be minimized or maximized, we have to find it out. Then for each variable some boundary is there, that is also here given over there. Then so this is all about that model of that function, that is optimization model for any application. Then with respect to the solution, we'll be having different natured solutions. The first one is feasible solution. Feasible solution is nothing but, so if you are having a problem, thereby we are aiming for the first two, that is the best one to get it. Whatever may be the solutions available over there will be taken as the feasible. That is the possible solutions to the problem, which has to satisfy all the constraints. But infeasible means if any of the constraints are not satisfied, then it will be considered as an infeasible solution. Okay. So here, optimal solution means among the feasible, first of all, basically it should be the feasible solution. Among the feasible solution, which is giving you the highest value, while it is maximized or while it is minimized. So that can be taken as that optimal value. And here, what I want to convey is, so because of it being an approximation problem, that means it is not an exact problem. Approximation problem, always these optimization procedures are, always we cannot aim for the best value, like the highest value, like 100. So near optimal value we can get it, but we can get the guaranteed optimal solution, but that exact solution we cannot get it. And that is after that solutions type, here we are going to have two other constraints, hard constraint and soft constraint. I'll tell you along with that application what may be those hard constraint and soft constraint. So here one of the models for this traveling salesman problem is given here. Hope you all would have seen this. So here also some of the constraints and the variable boundary and objective function is given there. You see here, you know the traveling salesman problem, n number of cities are there. One traveling person has to start from one city to another city. But here it is given as in the constraint listed, it is equal to 1, which means what? So theoretically, when we are looking at that problem, it is very simple. But when we are converting that into mathematically, here we have to represent that theoretical assumption into the logical view. Logical view in the means table form, tabular form. So in the tabular form, if you put one city to another city, if you take all the cities in row side and all the cities in column side, one city to another city, if you find the transit, only one movement should be there. So from that city to any other cities, you should not have that movement. So in that case, if you see in that row, only one entry will be there. So that is what that column wise and the row wise, it is given like xij is equal to 1 and I equal to 1 to n, xij is equal to 1. Hope you all can understand. So this is what giving you that path of that traveling salesman problem from one entry to another entry. The down constraint is giving you, so there should not be any subtour over there. I mean, that is, he is visiting all the cities, so that the cities should not be repeated. Here we are taking that the starting city is 1. So at any cost, one should not be repeated in that base. So this is to be formed. So that consent is being formed. So when you are looking at a theoretical problem, it is far easier to understand. But for converting into that mathematical model, you have to have thorough understanding of the problem statement. Otherwise, it is little bit tough only. The same way here we are having one another application. You see here, I have given that the course timetabling problem. This is well-known problem, timetabling problem. Daily we are working on this timetabling problem. So many entities are scheduled over the time slots, available time slots of either 18 to 8 hours for 5 days or 6 hours for 5 days, depending on this environment or depending on the institution. Here also we have to find out that decision variable, and we have to find out what is to be optimized. What is to be optimized when we are finding the timetable? So what are the factors are incorporating in this timetabling problem is mainly it is for the students that work is to be distributed. So their target is also to be satisfied, and the faculties that is lecturers criteria is also to be satisfied. It should not be violated, and that is the subjective priorities is also to be satisfied, and the classroom capacity also to be satisfied. It should not be surplus. That is, suppose 100 students are there, you cannot accommodate in that classroom, means it is not the best allotment, best timetabling allotment. So here in that way, if you see, we'll be having not only one objective function with respect to the different factors considered in this application, we have different objective function. So which means this type of problem is called as, since because of we are having three different objective function, this is called as multi-objective problem, multi-objectives problem. So these problems can be optimized once if you are optimizing all the three objectives in terms of lecturer, student, and also the classroom's criteria. And so as we know, after deciding that the design variables, we have to go for the hard constraints. That is constraints. Constraints means, when we are putting the timetable, we'll be having that is a time slot for each faculty to be given on each day. Then how many hours to be given for a subject. These are all hard constraints. So hard constraint means strictly that consent is to be followed. It should not be violated. So if we are creating a timetable, if this of the any of these consents is not there, you cannot say that it is not at all a timetable. Okay, but you can have one another relaxation is given to us, that is called as a soft constraint. Basically, it is a constraint, but the soft constraint is, so if we are satisfying all the constraints, then you'll be getting a timetable. That means it is a feasible timetable. It is a possible timetable. Okay. So if a hard consent is satisfied, now you'll be getting a feasible timetable. But if we are getting that soft constraint, that is, for example, if you have 4 hours for a subject in a week, or the 4 hours can be placed in a week, sorry, in a day, can be placed in a day. Otherwise, 2 hours can be placed in a day. There won't be any problem. There won't be any questions out of this also. But if you keep like that, that ultimate motive of the benefit given to the students and the teachers are not satisfied over there. So but that should not be given. So in that case, so some of the constraints, we have to give some gap between the lecture hours by considering the different entities involved here. So that is what called as soft constraint. So if you improve that soft constraint quality, it will be improving the optimality. It will be improving the optimality. If we are satisfying this hard constraint, it is violating the feasibility. It is violating the feasibility. So in these ideas, you have to look into the application to design that application into the mathematical model. So guys, if you have any doubts, you can ask me. I'm ready to clarify over there. Okay. So in the previous slides, we have taken well-known example of timetabling and traveling salesman problem. For converting that and for representing that into the optimization model. So here, some of the engineering applications are given there in different domains. You see, you have seen this structure. This structure is called a stress structure. So here, in order to get this structure, stress structure, you see how many rods are there in different sizes and different sizes. We have different shapes. This rods is there. So we have to keep them in an order so as to fit them in the right position. So for that, when we are looking that, we feel we are happy and we are surprising. So we are that is texting that is it is astonishing. But when it is been designed, what are the difficulties while it is been designed? So it is to be done in the best way. But this is what here that optimization is playing over there. That means before getting into the design of this one, we have to see the size of each and every rod which is placed over there. That is what the picture which is given in the right hand side of this entire architecture. Here see how many rods are there, in how many ways it is been getting connected, how it is to be extended. So for each and everything, correct measurement has to be taken over there. So this is what, by an example for understanding the structure, that is optimization in this engineering application. Another one is this in this automation. Here you see this car suspension. We all know well that suspension is very important for driving a car. So here, this is mainly depending on, that is in each wheel we are given with a spring and a damper. Okay, so based on the combination of these two only, you will be getting the good suspension. So here see, so that the design of this damper and this spring, how it is performing when it is moving, when the car is moving, that is what is given there. And some of the decision variables what they have used for designing this application is also given there. So here 4 degrees of freedom they are using out, that is a Q1 to Q4, that is the different forces which is applied based on the mass, based on the weight of that tire. So that is what been calculated in terms of Q1 to Q4. So all these calculations has to be effectively applied when that tire is being designed. So that only you can get a good response and a good performance when you are driving your car. And one other application is a vehicle routing problem. So here, suppose if you are in a depot, multiple routes are there, multiple vehicles also driven over there. So on what route, and that is how much distance, the shortest distance it has to cover. So with the minimum fuel and minimum time, minimum cost, how effectively we have to cross from one position to another position. So that is what can be decided by this multiple routes. Among that multiple routes, which may be the optimal route, that you have to identify. That will be automatically identified. This vehicle routing problem can be extended for our telecommunication line also. Wherever you have n number of nodes interconnected, so that way you can go along with this. So these are the some of the optimization problems. So that way, just I'm showing what are the design variables and what are the different objective functions for different discipline of the applications. Okay. Then following that, we are going for. So far we have seen about that optimization and how it has to be modeled for different application, and what are the different that is some of the applications with design and decision variables that we have seen so far. Now we are entering into the optimization problems. Okay. So here our target is about we are aiming for mapping this optimization algorithm for the engineering application. So optimization algorithm is based on the optimization problem. I mean that problem, existing problem. The problem is nothing but that is it is mainly decided by the data. It is being generated in that problem. For example, if you are having the student in your college and the student are numbered as 1, 2, 3, that is integer numbers only. You cannot go for that real values. In that way, if it won't be considered as binary also. So in that way, mainly that data is deciding the property of this optimization problem. And the data movement is also deciding that property of that problem. Okay. So based on this property of the given problem, only you have to identify among the what type of, that is the n number of optimization algorithm, what is suitable for that type of application. So this is what the way where technically you have to play your role clearly to fit this algorithm into the application. Here you see, these are the different variations of these problems, non-differentiable functions and constraints. It is opposite to differentiable functions. So if we are able to differentiate any one function, then you know that the differentiation is nothing but so finding the change rate, that means dy by dx is nothing but x is one term, y is one term, x is that is independent variable, y is dependent variable. Okay, so with respect to x, we are deriving that of y. I mean rate of change of x with respect to y. We are finding that out of that dy by the rate of change of y with respect to x. We are finding out of that dy by dx. So if it is differentiable, then you'll be getting the smooth curve in the, I mean smooth movement of the data position movement. But if it is not differentiable, then it will be giving you the straight line structure. So in the straight line structure, finding the optimal value is totally different from finding the optimal in the curved structure. So thereby, what I wanted to convey is the optimization algorithm, what you are planning for this non-differentiable function is different from differentiable function. In that way, you have to identify. Not only function, constraint also can be non-differentiable and differentiable. So the variation in terms of this constraint and the functions. So here, don't think that this function is literally meaning that mathematical idea. This is nothing but giving you the movement of your that is that values in the problem. That is attributes of that problem. In general, it can be considered like so. Then discontinuation function and the search space. If it is continuous, that is different. So you can easily search from one place to another place. Your searching moment. Discontinuous. So according to that problem, you have to find out what type of optimization algorithm is suitable. In that way, discrete search space, I mean continuous search space is also available. So mixed variable, the different types of mixed variables is there. Then in a problem, you may have these three variables. Not only number of constraints, number of variables, each variables are having its own nature, its own that is what to say, its own type. Then large dimensional problem, if it is increased in terms of variables and constraints, then non-linear, linear, two things are there. Non-linear means it's giving you the wide spread of feasible boundary domain. Linear means it is increasing in one direction. That is like a straight line movement, it will be going on. So that non-linear, so literally saying, if you have an equation or any function in terms of degree 1, it can be linear. If you have more than 1, like 2, 3, 2 means quadratic, then more than 2, if it is going on, then that is a non-linear. You see x is x power 3, upon 3 values of x will be there. So that means its spread is it's wide. That means in and around that particular object, that feasible solution is spreaded over. So among there, we have to find out the best one. Then multiple objective, then uncertainties in variables. So uncertainties in variables is the important factor to be considered in the recent trend. Then why means in the artificial intelligence area, so certainty is the vital role, is playing vital role. So uncertainty, suddenly the variables nature may be changed. Sometimes if today without any announcement, today it is heavy rain, heavy storm is there, something is there, total setup is to be changed. Accordingly, everything has to be made it up. Then computationally expensive problems. So these are the factors to be considered while we are looking for finding the optimization problem. You see here, in the right hand side, I have given for your understanding, that is in the position displacement, how it is getting into the different levels when it is being derived. That is dy by dx, d square y by dx square, like so it is going on up to d power x y by dx power 8. Okay, dy by dx, you know, velocity, acceleration, if you are increasing, then it will be giving you. So then, so again, if you are differentiating with respect to x, again you are having some other terms like jerk, snap, crackle, and pop. You see, velocity and acceleration. Velocity is the normal way to be going. Acceleration, if you are speeding, that is a speed up with the work, you have to accelerate. That is the literal meaning of that acceleration. And then suppose if in the smooth way, if you want to go up to acceleration, we have to stop. If any jerk is there when you are driving, that means the smoothness is not there. In the rough area, if you are going to search for the optimum value, then you have to go for the third derivative. That's what I wanted to convey you. And pop, snap, crackle, all these, when you are driving, you will be facing all these factors. So suppose if in a rough terrain, if you are moving, your vehicle is moving now, you'll be getting that crackle sound and pop sound, that is popping is there. So all these factors will be raising if it is not the smooth movement. So based on that movement also, we have to decide what type of that is the derivative we have to go for in the differentiable functions. So these are the structures which is helping you to understand, that is what are the different properties of functions we have looked so far. So here the different types of optimization problem is given over there. That is deterministic optimization versus stochastic, continuous and discrete, unconstrained and constrained, one, none or many objectives, and local and global, local search and population-based optimization. Then finally that combinatorial optimization. So deterministic optimization is nothing but if your data is known to you, what you are aiming is known to you, then that is a deterministic. If it is not known, randomly you are searching, you are aiming for wherever you are looking ahead, then you are taking your step and you are working for, then that is stochastic. Continuous, discrete. You see, these are the ways that optimization can be done. Unconstrained, constraint. In the previous model, we have used some constraints, but in the unconstrained model, without a constraint, your searching will be there. Even if you, so thereby in the previous one, we have seen about the nature of that problem. But here we are looking for the nature of that optimization. When we are designing your optimization algorithm for the engineering applications, these are the factors to be considered. Here, the one of the idea is local search and population-based optimization. This is what recently we are all working on. That is, local search is nothing but the locally for the best one we are finding. Not only that, so here the searching element is only one element. We are starting with only one element. From there, with where a continuous trajectory will be entering into the next level. But in the population-based movement, so initially we are taking the population. So thereby, by doing some changes with some operators with respect to the application or with respect to the algorithm, we'll be getting into the next generation. Then again, next generation by making some changes, like so, we'll be moving on to the next generation till you are getting the best one population, best one member in that population. So this is what the different types of this optimization problem. So here, whatever may be the optimization problem and whatever may be the optimization algorithm, we have to think about the three factors like objective function, variables, and the constraint. As we all know that the variables are going to be continuous and discrete ever, and that constraints and objective functions are going to be linear and non-linear. So before going to design all these things and fix up all these things for any of that application, you have to take care of these factors mainly to decide what application and what algorithm for. Okay, so this is what the different optimization types just before I told you. You see here in the line search method, just one curve is there, no constraint it is working. I mean unconstrained optimization. So if that gap is, that step is increased automatically in that boundary, like here and there. Suppose if you have even a curve-like structure, if you put a ball with a high speed, then it will be movement like this. Slowly, if you are moving in a string, then it will be getting down like this. So these are some of the examples you have to understand when you are going for this unconstrained optimization. And in the constraint optimization, so though that cone-like structure is there, that is the only area where you can looking for your best one. And multi-objective optimization. Multi-objective optimization. So here multiple objective functions are there. F1 of x, F2 of x, F2 x, Fx, k of x. So in the previous slides, I have told you about the timetabling problem. So thereby for the different entities come over situation, we have different objectives. So those objectives are to be identified, to be listed in this multi-objective problems. So here you see that diagram. So thereby so many feasible points are there, and that is that different balls, different circles with light blue, dark blue, yellow, and red is shaded up. That is, light blues are saying that it is a feasible point. That means all the constraints are satisfying by those points. That means feasible points. Then that blue is also a feasible point only. Then beyond that blue is infeasible point, and then utopia point. Thereby you have to get that is in the x-axis objective 1, y-axis objective 2. In this diagram they have taken only 2 objectives. If you are taking for 3 objectives, then 3 dimensional you have to add it up. So here you see that objective 1 and objective 2 need not be the same optimization, like need not be the same minimum. So one may be minimized, one may be needed to be maximized. But there also again problem comes. Okay, suppose if you are working on a system, so in your system, what are you expecting? That is, your time is to be decreased, but efficiency to be increased. Upper time decreased na minimum of time, efficiency to be increased na then maximum of efficiency. Even when we are booking our air ticket, we'll be looking for less time but high, that is a less amount, high speed. So for these two are inversely proportional, inversely related. For those two things, different objectives are there. For different optimization is to be applied. So even in single problem, you see there pair to friend. Pair to is the person, he has identified this multiple objective optimization idea. So that's why this is called as a pair to friend. That is, so that lined dots which are connected with that line, the dots which are connected with that line shows that that is also feasible, but provided that so that the topest one is satisfying that objective 2 highly, the least one is satisfying the objective 1 highly. But here we have a payoff between this objective 1 and objective 2. But what we are looking for is should satisfy objective 1 and objective 2 simultaneously. In that case, since it is a minimization, the minimum values are that corner values only. So that is what that pair to front return values can be taken as optimal solution of this problem. And then single objective and multiple objective. If it is a single objective, you see only one objective is there, that is f is there. Multiple objective function, that is you are getting the space whereby you have to obtain the best one. Combinatorial problem, if you are given with only one variable, it is fine. But if you are aiming for multiple parameters to be combined in a single solution, you see here, this is what the different thing, that is the score and the prices of each items are given. So what item can be taken with the specified amount? That is what that combinatorial problem. N number of items are there, along with their prices also there. So when you are going for ordering those, you have to identify with your available cost how efficiently you can order. Since because here 3 or 4 items are there, you can easily identify. Suppose if n elements are there, how it can be identified? That is what the problem among this combinatorial problem optimization. Then, as I told you in the local search optimization, that curve line show you that that search starts from only one point, then gradually based on the movement of our application, it will be moving from one line to another line. But here you see so many curves are there, ups and downs it is there. Sometimes it is reaching the topest, that is highest position, then after that it is coming down. So when we are working on stock, you may know that sometimes it will go high, then later on it may not reach that, it may not reach that position. So upper local, so upper in that duration for 5 days or for 1 month, what may be the best that you can take and do your operation? That is what local minimum or local maximum. And the other one is global maximum. Population based optimization. So here the main difference is that is we are starting with one variable now, that is a local based. If you are instead doing so, if you are starting with the multiple items to find the best one, means then it is been population based. For example, you know that is particle swarm optimization. That is nothing but n number of swarms are there. That is particles or birds are there. They are trying for finding their food at the minimum distance. So all the particles are moving. That means they are that is nothing but a population. So they are moving towards and their direction is getting changed. So thereby also from one location to another location, how it is getting moved. how it is translocated, that is been identified by its nature. So that's why those algorithms are called as nature inspired algorithms. So here, from one level to another level, in order to move from one population to another population, in order to move, some operations is to be applied on that solution in the population. Then we'll be getting the new generation. Then again, we have to find out whether it is okay. We are satisfied with our objective. Otherwise, we have to proceed further. Okay. So finally, after looking all about here, what I am summarizing the different types of optimization, how far it is interconnected, that is among themselves. Like though we have seen so many things, single objective, multiple objective, for those two different objectives, what are the different? I mean, here you see both discrete and continuous variable. Discrete and continuous variable we are using here. In that case, what may be the optimization algorithm can be applied for? So that is what the continuous optimization. I mean, continuous variables can be used with the unconstrained and also continuous and differentiable objective functions, and also randomized optimization. Apo one that is a nonlinear constraint with the continuous optimization. If you have, then you can go for these different types of optimization. Apo from the available so many optimizations, finding out the best out of the problem is the challenge in this that is mapping of optimization algorithm into the engineering application. And moreover, above all, the basic thing what we are lacking, many of us are lacking in our research work is we should know how that solution can be coded, that is encoded. Okay, I mean how it can be represented. So we are saying theoretical story about this is what we are doing, that is what we are doing, but when it is being actually implemented, we should know how effectively we are representing. So here, as I told you, the different representation of that variables we have considered before, that is a binary, real, integer, and permutation is nothing but a combination, sir. Then in that combinatorial problem, we will be having this type of representation. Suppose if you take that traveling salesman problem, yes, solution is like suppose 3 cities are there, 1, 2, 3 cities are there. So 1, 2, 3, 3, 2, 2. This is one solution, and 1, 2, 3, 1, 2, 2, 2, 2, 3 is another solution. Okay, so in this way we'll be having a combination of that all items should come in that single solution. That is what that permutation representation. These boxes are representing only one solution. Okay, so in binary terms and real terms and integer terms we can have. Okay, so this is very important when you are feeding your data of your application into the optimization model. And recently we are having so many optimization algorithms. Here SALP, SWAM, Moth Frame, you can go through, all these are available in the web. So here also you have to try out with see, many of them are trying with different combinations of algorithms, and they are saying that this is what performing better for our applications like so. That is not the real way of doing that application, doing the research work on this that is optimization on any of the optimization for any of the applications. Here you have to find out what type of problem it is. So based on its data and based on the constraint and based on its boundary, based on its variable, you have to identify how it can be modeled, and based on the property of the problem also you have to identify. So that is what we have seen so far. So based on that, you have to identify from the out of n number of available algorithms which can be the suitable one. Here see, so after all ideas about that optimization, here I have given how come that machine learning and optimization, I mean this in the latest trend of machine learning is being incorporated with this optimization. That is what is given here. So here you can see in many places this optimization is taken place. That is you see that machine learning model, when you are doing that, you'll be having a neural network model. Actually thereby we are finding for the best one. Am I correct? That is, after training the model, if you are giving your data, we are checking for whether it is being predicted correctly or not. Upon that production is that is it's doing correctly. How far efficiently it is doing, 100% is correct. It has to do. That means that is optimization only. Upon what you have designed that machine learning model is to be then optimized model. If it is not an optimized model, you may not be getting that right solution. I mean right prediction. So thereby also that optimization is there. So here, how are you defining that model? Number of input is there, number of hidden layers are there, then finally output layer is there. Then in the output layer, what are we looking for is that is that difference between that is the two values, errors between that actual value and the expected value to be minimum. That means it should be 0 till you are getting that it is to be repeated. Okay, so in that way we are aiming for optimizing your model. There also one optimization. So since in terms of function we are doing that optimization, this is called as a function optimization. Then function approximation is coming over there. What is that function approximation? After creating that model, what are we doing? That is creating that model is nothing but training that model. Okay, after training that model, we have to test our model. I mean, we have to work on that model. So when we are working on that model, what are we getting? So we are what are we saying? What are we doing? Actually, if you are doing on your own, how are you saying that it is working fine? If it is predicting, or if it is classifying, or if it is clustering correctly, you are saying that it is working fine. That means what? Your testing data has to be given correct result. Okay, wow? That means approximation. So it is not giving you the 100% the best result, nearby that best. I mean 99, 98. So that this is performing that approximation also. That is a function approximation. So these are the two main area of optimization which is taken place in our machine learning. So which means what I wanted to convey is no area is left out in our field, in the whole world, without this optimization. Even any trend of any latest innovation we are finding, so thereby we have to look for whether it is working fine in all the situations. That is optimization. Then here, these are the different algorithms which is taken place in your ML. So linear regression, and when we are predicting something, I mean whether your model is predicting, giving you correct result, so thereby linear regression is performing. Then logistic regression, for classification we can go for this. So thereby in turn one algorithm, that is iterative local search algorithm. This is what that optimization algorithm. So here what I want to convey you is actually the work is machine learning. Okay, though it is a machine learning, they are finding this algorithm, I mean iterative local search algorithm, in this place to get the classification pakka. That means that area they have identified thoroughly what type of algorithm is suitable for this type of a situation. Property of the problem they have identified thoroughly. That's what even I am wanted to convey you. Then neural network. So here in neural network, n number of times back propagation feed forward, n number of ideas it is to be repeated, so that iterative global search. Then hyperparameter. So thereby we are trying for different combinations of parameters, that is also to be tuned. That means these are the places where we are having our this optimization in ML. Then finally, so I have given the representation of these features. So this machine learning, if you take that machine learning, so it's been working with the features only. So whatever data you are inputting, we have to give the values to that input. Suppose if you are giving that images, means in terms of the CNN, it is automatically extracting the features. If you are working on ML, you have to extract the features from the images and we have to give it to them. And now we have to identify how that images are represented in terms of features. What are the features you are using and how it is being represented? All those things you have to get a thorough knowledge about it. So thereby feature engineering is coming. So thereby mostly we are using that is one hard encoding technique. So if that listed values are there, I mean enumerated values are there, so whatever value is available in your data set, that will be marked with 1, otherwise it will be marked as a 0. So this is the way these features are represented. And so here in Python, open and see if you are implementing, how come that arrays is helping us to input that image into the machine learning model. So these are the different solvers which can be applied for optimization in different domains, and these are the taxonomy of these optimization methods, starting with the continuous and the combinatorial. So many flow is available, that is up to your convenient, and you can get your flow also, but the thing is that the main core of that concept is should not be violated. So I mean, what I want to convey is non-linear, linear, under linear, simplex and intermediate points which has to come. Under non-linear, global and local search has to come. So these should not be changed. Where you are keeping this non-linear, linear is immaterial, but that the flow of that idea should not be violated. And in this combinatorial, sometimes we are getting that exact and sometimes we are getting that approximate. In n number of solutions are there automatically, when the size is increasing, we cannot go for that exact solutions. We will be having that approximation method only. So thereby we are going for that heuristics, meta heuristics of these ideas. So these are the highly remarkable points on this optimization techniques. So mainly among all these things, that is constraints, and one application, one problem cannot be applied for all applications. Then that is discrete variables. We are having so many difficulties, uncertainties when you have on the variables. All of the sudden we cannot find. I mean, so if you have any continuous line, it is okay. And that is if you have discontinuous search, then where are you starting? Where are you ending up? Where are you starting? From where to move? I mean, you are walking on your way. So abrupta, somebody asking you to stop, and they are placing you to somewhere. From there, they are asking you to start your walk. Then, do you know where to move, how to walk, how many steps to walk? If this is done manually, a little bit, though it is confusing, we can manage. But because of it is to be done automatically for our application, for the discontinuous data, so working on this is very tough. Then uncertainty, that is what that uncertainty is also. Then noisy and dynamic optimization problems. Then other thing is multiple objectives of optimization problems. In multiple objective optimization problems, since payoff is there between multiple objectives, though you are getting the best result for X objective, it may not be giving the best result for Y. What can be taken? We have to compensate only. Compensate for X and Y. In between that the highest value of X and the highest value of Y, what may be the compensation that we are looking for, and we are giving that as the best one. Though it is not fully satisfying X, fully satisfying Y, because of that compensation property, we are taking that middle one as the best solution for that problem. Then, so here, so among all these, what we want to conclude is we wanted to have innovative and flexible optimization algorithm for satisfying all latest issues we'll be facing in the latest technologies. So up to this, hope those who have listened, I have given the maximum to understand how effectively this optimization algorithm is to be applied on the different applications. So up to this, let me stop my presentation.
Any questions from participant side? Any questions? You can raise a
Yes, if you have any questions, you can raise me now.
Ma'am, Nandhini
Yes,
ma'am, has given a
yes,
very
ma'am.
nice and clear presentation, ma'am. And it is an excellent session on this optimization algorithm in engineering application. You are given with a high clarity of explanation, actually. Thank you, ma'am. Thank you very much.
Thank you, ma'am.
Thank you, ma'am. Ma'am, you can wind up, ma'am. We are
Okay.
moving to the next
Okay,
session.
thank you, ma'am.
Thank you, ma'am.
Thanks for giving me this opportunity, Indra.
Okay, sure, ma'am. Thank you, ma'am.
Thank you.
Participants, we can move for the presentation. Please get ready for the paper presentation. Right.
I hope disconnected.
Yeah, no, ma'am, you are connected.
Stop incoming video, remove spotlight. This.
Like, first candidate.